morning, everyone. Today we're going to be looking at how to resolve problems under bending moments and shearing forces. Now, in structural mechanics, there are two components that are very important when it comes to structures, which are the moment induced by forces, which are mainly shearing forces. So, the first two problems we're going to be looking at in this section are two types of beams. Remember, we have discussed about structural members, and we discussed that we have a structural member called a beam. So the first thing you have to do for me now is to ensure you subscribe to this video, to this channel, and also on our notification bell. Make sure you subscribe. That's the first thing you have to do now, because the more we see subscription, the more we have the energy to do other videos. So this chapter is just introduction to this topic, which is the bending moment induced by beams and the shear forces. Remember, what we are looking at in this place are just determinate problems. We are not looking at indeterminate problems in this section. So we are just looking at simply supported beams and cantilever beams. Now, a cantilever beam is a type of beam that is fixed at one end and free at the other end. So look at this beam that I have here. Look at the support. It has only one support, which is a fixed support. So it is fixed at one end and free at the other end. It's a determinate problem, and it has just three reactions which can be resolved by the static equilibrium equations. So we are going to learn how to resolve the bending moment, we resolve the shear forces, and we also learn how to calculate or to draw the bending moment and shear force diagram. So there are things you have to know. Now, basically, we are going to be looking at two types of loadings in this section. We're going to be looking at what we call the uniformly distributed load and the point load. Like, for example, now this is the point load that is just acting at the point, a particular point. But there's a load that is uniformly acting at a particular amount of distance or a particular area. We call them uniformly distributed load. For example, now let's say we have a load that is starting from this place and it ends here, and it's acting all over this length. Or it's acting at a particular length at the same time. So that is, we call it uniformly distributed load. So also know how to draw the bending moment and shear force diagram for that. So for this, we want to draw the bending moment and shear force diagram. For point loads, we have a way of doing it. For uniformly distributed load, we have a way of doing it. So I'm going to look at two problems: how to draw the bending moment and shear force diagram for point loads and uniformly distributed loads. So let's start from this question I have here. The question is from the beam below. Draw the bending moment and shear force diagram. Draw the bending moment and shear force diagram. Already said this is a cantilever because it's fixed at one end and it's free at the other end. So the first thing I'm going to do for me now is to show the forces that are acting. Show the forces that are acting. So let's draw the free body diagram. That's the first thing. Solution. So we are going to draw the free body diagram of this beam. So we have three reactions in this place. We have the horizontal reaction, we have the vertical reaction, and we also have the moment about this point. So let's get point A and let's get point B. So this is the for the horizontal vertical reaction at point A. This one is horizontal reaction at point A, and this is the movement at point A. So there's no other support there. So this is what we have, and look at the beam, and it is carrying a point load, just a point load that's acting at a point, and the load is just 2 kilonewtons. That is the value of the load. And what is the length of this beam? The beam is of length 5 meters. That is the length of the beam. So the first thing we have to do now is to calculate the shear force that is acting on this beam. So how do you calculate the shear force? The first thing is to obtain the shear force. Let's obtain the shear force and see what we are going to have. To obtain the shear force from this beam now, we are going to start from where the forces are. Then we move from that place to the end of this to this support. We're supposed to move from one support to another. But since we have so many issues here, we cannot start from this place. Let's start from this free end. It's very good, or it's very advisable to start analyzing a cantilever beam from the free end. That is the best way to analyze a cantilever beam. So let's start analyzing from this place. So at point B, remember this point B and this point A. So okay, let's for the shear force. Shear force acting along the beam. For the shear force, now you know, okay, shear force at point B. What is the value of shear force at point B? We have a load of 2 kilonewton acting downward. So you can say, okay, let's say if the load is going downward, it will be negative. If it's going upward, it will be positive. So let's do that way and see what we're going to be having. Now let's say, okay, since this one is going downward, let's say shear force will be minus 2 kilonewton. That is the shear force at point B. That is shear force at point B. Now let's check. If you look at this horizontal reaction, it will be latent in the sense that it is not active. Why is it not active? Because there is no horizontal loading, so that will not disturb anything. So we can just go on and keep on analyzing. So this load, if you move, then anytime you see any load, as we have another load here now, we will still include it. But since there's no other load here, you now come to this place. It's okay. At this point, you have ROV. You have ROV. Do you even know the value of ROV? No, we don't know the value of ROV. Now let's calculate the value of ROV so that we know ROV8, so that we know the value of ROV. Remember from the static equation or equation of movement that upward reaction will equal to downward reaction. So which reaction is coming up? ROV is going up, and it must be equal to which reaction is going down. Which force is going down? And 2 kilonewtons is going down. 2 kilonewtons. So ROV is equal to 2 kilonewtons. So when we get to this point B, we met a force going up. So any force going up should be positive. So shear force at point B will be equal to, now shear force at point A. So this place is point A, this point A, this point B. So shear force at point A will be equal to this one that is going up. So that will be the minus 2 that is already coming plus this 2 that is here plus that 2, and that will be 0. So the shear force, the total shear force that will be at point A will be 0. So I'll show you how to draw this diagram so that you see it. So the shear force will be this one that's already coming plus this ROV, everything will land at 0. So that shows that we're already going. Yeah, we're already moving forward. Things already going well. Then now let's look for the bending moment. Then when you move from, so okay, we can also do it like this. We can also say shear force from B to A. When you move from B to A, you move from B to A. Then shear force from B to A will still be minus 2 kilonewtons. Why? Because from B to A there were no loading. Then at point A now you now met a 2 kilonewton going up. So the one going on is positive, the one coming out is negative. If you add positive and negative together, it will give you 0. You want to do it like that. It's also known as that. So bending moment. For bending moment, what are we going to have? Now we have to do for bending moment. You can just come and say, okay, what is the bending moment? What is the bending moment? At point A. Okay, at point B. I said you start analyzing from the free end. It's very good to start from there. What is the bending moment at point B? What will be the bending moment at point B? Now, for point B or at point B, the bending moment will be, now what is the formula for moment? Moment is equals to force times the perpendicular distance. Force times perpendicular distance. That is the formula for moment. Now at this point B, what is the distance between this force and the point we are taking the moment from? Now the point B, the force is acting at point B, so there's no distance at all. So if the distance is 0, the bending moment will be 0. So at point B, the bending moment is 0. So we have 0 Newton meters. That will be kilonewtons meters. So we are using kilonewtons. Then there's no other point. They will now get to point A. Now at point A, bending moment at point A. What will now be the bending moment at point A? What will be the bending moment at point A? Now the bending moment at point A will be this 2 kilonewton times the distance, the perpendicular distance between point A and these two that we have here. So that will be 2 times. Now what is this? Remember, it's negative. It's minus because it's going down. You take note of that. It's very important. So remember, this thing is going down. So if anything is going down, it should be negative. That's why I just put negative sign to that too. So now what is the difference between this point and this A? 5. That is perpendicular distance. So this one will make angle 90 to this point A. So that will give us 2 times 5. That will be minus 10 kilonewtons meters. That's what we're going to have as the moment at point B. So point A. So the next thing we have to do now is to draw out the bending moment diagram and the shear force diagram. So what you just do, you draw out the beam. It's very important to do it this way, or it's very nice to do it this way. You draw out the beam. Then we have a load of 2 kilonewtons. We have a load of 2 kilonewtons RT. So let's just trace a line downward. Then let us draw out the first one, which is the shear force. For the shear force, you just take a line for the beam. Let's see how the shear force is actually distributed along the line. So okay, at this point B, what was our shear force? Our shear force at point B was -2. So measure -2 downward the straight line. Just measure downward the straight line. So that'll be, let's say that is -2. Then from B to A, the TT remains as -2. So when you move from B to A, the TT remains as -2. So when we get to A, so when we now get to A, it will clink at 0. So we go back to the origin. So when we get to A, the thing moves back to 0. So here's what we're having now as our bending moment and shear force diagram. Just taking a rectangular shape. So we have minus here. You can just shade if you wish. Just shade this. So this will be our shear force diagram. This will be our shear force diagram, and the value for this weekend is 2 kilonewtons. That is the value for that place. This is 2 kilonewtons. Now for the bending moment, I just draw a line downward. Now when bending moment is negative, you can draw it to the up side, you also draw it to the downside, depending on if you are drawing it on the compression side or if you are drawing it on the tension side. So for bending moment now, I will be taking the negative side to the upper side. I will draw it to the upper side, the negative side. I will draw it to the upper side. Then the positive side, I will move it to the downward side. That's how I'm going to be doing it now. So let's check and see what we are going to have. So then we're going to take a line. Yeah, let's say that is the point B. So at point B, what was the bending moment was 0. Then at point A, what was the bending moment? The bending moment was -10 kilonewtons. You just draw -10. You can also draw it downward. There's no problem about that. But maybe if you draw it downward, you say, okay, I'm drawing it on this side or on the other side. So let's measure 10 to the upper side. From here to here, 19. Just mark it. It will be 10 kilonewtons meters. Just draw that. Then between this point and this point, now if the load is a point load, we join the 2 points together with a straight line. If the load is a uniformly distributed load, we join the 2 points together with something like a parabolic curve. That's how we do it. So since the load is a point load, I'm going to join the points in a straight line. I'm going to join the 2 points in a straight line. So that's what we're going to do. So we have something like this. This will be our bending moment diagram. So this is negative actually. Even though it's right downward, you still put negative there. That shows that it is negative. That is the major thing there. Not one positive. So this will be our bending moment diagram. So that's what we're going to have. This is shear force diagram, and this is the bending moment diagram. So for the example 2 now, I'm going to show you guys how to draw bending moment and shear force diagram for uniformly distributed load. That is the next one we're going to do. So let's look at the next example. So the example 2 we are going to be looking at is a case of a uniformly distributed load. We are not looking at the point load. We are done with point load. We want to look at the uniformly distributed load. Now, the uniformly distributed load is a type of load that is something like spread over a given distance. Like spread over a given distance. And you can see we have 50 kilonewtons per meter run. So this load you are seeing here is spread from A to B over 2 meters. So this example of a uniformly distributed load is the same all through. The value of the load is the same, but that's why it's uniform. You see, I have varying load. We have the one that is uniformly varying. Maybe we start from here, we vary to this place. This place and this place will not be the same. We have some that will just be something like irregular. It will just be varying, coming down, come up. But for this case now, we're looking at just the one that is uniformly distributed over a particular distance or even a particular span. So the first thing now is to draw out the free body diagram. We already know the reaction that are occurring in this. I told you if you want to analyze a cantilever beam, it's very good to start from the free end. So let's draw out the problems that are associated with this support, because this is a fixed support. So we are going to have horizontal loading, although the horizontal loading will be latent because then we have the vertical loading at point A. We have the vertical loading at point A. Then we have the bending movement at point A. We have the bending movement at point A. Bending movement at point A. And this is the beam. This is the beam. Let's see that as the beam. So this point B, this point A. It has a load of 50 kilonewtons per meters. So the first thing we're going to do is to calculate ROA. Something like ROV, because ROH for the horizontal direction is 0 because there's no horizontal loading. Then we can calculate ROV now by using some of the upward forces equal to the sum of the downward forces. So our ROV is the upward force going up, so our ROVA will be equal to the downward force, which is what? 50. Now, is this not a force yet? No, it's not a force yet. Why? Because it is in per meters. So unless we are told to leave our force in per meters, we are not free to do so. The unit of force, the dimensional unit of force, is newtons. Something that will give us in newtons, which is force mass times acceleration, which is MA, kilogram per second squared. So that is also a newton. That is something like the main unit to use for force, in case you don't want to use the unit that is coming from dimensional analysis. So this one is not in newtons. Kilo is just 10 to the power 3, so that is not a problem. That is a value in physics. But this meter should not be there. It should be either kilonewtons, meganewtons, or in newtons. So how do we remove that meters? So we convert it to equivalent point load. So how do we convert a uniformly distributed load to an equivalent point load? We just use the value of the load to multiply the span or the distance or the length of the load. So what is the length of this load? The load is start from here to here, and the length is what? Is 2 kilonewtons. So we are going to use to multiply is 2 meters. So we're going to use this 50 to multiply this length is 2 meters, that's 50 times 2. And that gives us 100 kilonewtons meters. So that will be the, there's no meters again. Since we already use it to multiply this meter will go to this meter, only kilonewtons will be left out. So the next thing we're going to do now, we're going to calculate the shear force from B to A. Now so now we can draw out the shear force diagram. So for shear force, the first thing we draw out, calculate our shear forces. Calculate our shear forces. So how I'm going to go about that? So let's check. We have point B, we have point A. So we're going to calculate the shear force at point B. So if you want to analyze the cantilever beam, always start from the free end. It's very good to start from that point. So the shear force at point B, and you naturally okay. We said the value of this load is the load itself and distance. What is the distance between this point B and this point? There's no distance. So since there's no distance between the point, that load is starting from that place. The shear force at that point will be 0, which is the load times 0, because the distance is 0. So the shear force at point B, since the load is starting from here, and there's no distance between this load and this point. So there's no distance to compare with. Multiply this one with 0 with 0. So we're going to have 0 kilonewtons. That's what we're going to have. And the shear force at point B. Now, what about the shear force from B to A? From B to A. What is the shear force from B to A? Now we now move from B to A. What will be the shear force? The shear force will be minus 50. Since it's coming down, so the when something is coming down, we'll take it as negative. So since the load is coming down with minus 50 times the span. and it's span. So what is span of this B to E? That is 2 times 2. That will give us minus 100 kilonewtons. So that's what we're going to have. Now what will be the shear force at point A now? What will be the shear force at point A? Now at point A, when you move from B to A, you meet a load which is going up, and that is 100 kilonewtons. So we are going to have minus 100 plus, that is minus 100 that's already coming, plus this one that's at A, which is what? 100 for ROA. That will give us 0. So the thing will end at 0. So that means we're already in the good direction, already in the right direction. So for bending moments, so what we are going to do, we're going to try to bend this beam. So what are we going to get for bending moments? So let's check. Bending moment at point B. We're going to look for bending moment at this point and at point A. What is the bending moment at point B? Now the bending moment at point B, since there's no distance between this load and that point, the bending moment at that point will be 0. So bending moment at point B is 0 kilonewton meters. What is the bending moment at point A? What will be the bending moment at point A? So this one is still a very vital thing you should take note of. How to calculate the bending moment induced by a uniformly distributed load. So look at what I'm going to do now. What we are going to do? I want to calculate the bending moment at this point. So what is the distance between? We don't even know where the load is. The load starts from this place, and the load is still here. You can see the load is even still here. So we don't actually know where the distance that we go to multiply the load with. That is the problem. So that is the first problem we have, because the load is everywhere. So we want to say no force times distance, and the load says this one is not a force. So look at what we do. The first thing we do, we will convert this load to force. I already showed you how to convert the load to force. Use the load to multiply the span of the load or the length of the load. That will give you the force. Now, the force will not be acting at somewhere. Where will the force be acting? It will be acting at the center of the load. That's where the force will be acting. We are at the center. Now, what is the center of 2? The center of 2 will be 1. So we are at something like a point like this. So look at what I'm going to do. So the first thing, we are going to have more force and resistance. What is the force? The force is that's minus 50 times 2. That is the force. Why? Because this is in kilonewtons per meters. We have to convert it to kilonewtons. The first one we use to multiply the length of the load. That will provide the force. Now, if you not convert it to force, the load itself will not be acting at the center of the full load. Let the load move from here now. The load move from here to here. And this was the load. If you convert it to force, the thing will be acting. The force will be acting at the center. If the full load is 2, from here to here will be 1. So the load will be acting at something like this, which is 1 meter. That's how the load will be acting if you convert it to force. So what is the distance between this place and this place now? Will not be 1. So what is half of 2? 1. So times 1. So we will have minus 100 kilonewtons meters. So that's what we have at the end as the moment at A. That's what we have here as the moment at A. So the next thing we do, we'll draw the bending moment and shear force diagram. So how do you draw the moment? First of all, draw the load. Very nice. It's a nice if you draw the load out. So draw out the diagram. So draw the diagram. Let's see do. Draw the diagram. Then you have the load on top. And the load on top. Then we'll have here 50 kilonewtons per meter. So that's what we're having. And the distance is 2. Distance is 2 meters. This point B. For this place point A. So you can just draw. If you want to do this, you use a graph. It's very important. It's nice. It's a nice thing if you use a graph to do it. Graph it. So we'll have to do like this. We'll have this. Then let's for the shear force, you draw vertical axis. So you draw maybe the beam as the horizontal axis. And let's check how the shear force is distributed. At point B, shear force is 0. So at this point, the shear force will be 0. Then let's check at point from B to A, the shear force now rise to minus 100. So from B to A, the shear force moves to minus 100. So we're going to mark out minus 100. Mark out minus 100. So 100 will be here. Because it's the other side. Now for shear force, we follow as something like the normal Cartesian coordinate load. upper side will be positive for y, the downside will be negative for y. But for bending moment, you are going to interchange it. You draw the positive side in the negative axis. Then you draw the positive moment in the negative axis. You draw the negative moment in the positive axis. That's how we do it. You are drawing bending moment. That will give us, if you draw it that way, that will give us a real structural application or knowledge of what we are doing. So that will be very nice. But if you can also do it, you can also draw the positive in the positive side, draw the negative in the negative side. It won't change anything. The value of the moment will still be the same. But the other one will just give us a real structural view of what we are doing. But for shear force, it follows. So we're going to have 100. So we have 100 kilonewtons. So at point A, now the shear force at point A now comes to 2. So we're not having shear force at point A as 0. So what you do, you just join the straight line. Join this and this with the straight line. Just join this with the straight line. Then you join this with the straight line. So that will give us the shear force diagram. This is a straight line, please take note of that. It's very important to take note of that. So that is negative, that will give us the shear force diagram. The shear force diagram. So now let's go back. Let's go and look at the bending moment diagram. This is shear force diagram. So now let's look at the bending moment diagram. How do we draw the bending moment diagram? So same thing. We can also draw out our beam. So we come. What is the bending moment at point? What is the bending moment at point B? Bending moment at point B is 0 to mark. Is bending moment at point B. Then what is bending moment at point A? Minus 100. Bending moment at point A is minus 100. So what do? You mark out minus 100. So it's negative. Destroy to the positive axis of y. So you just come to this place, mark out 100. So from here to here now, it's 100. You measure it, it's 100 kilonewtons meters. The next thing, you won't join with a straight line for a uniformly distributed load. You will join it with a straight line. You will join it if the load is, to point load, you join with a straight line for momentum. But if it is a uniformly distributed load, you will join it with a parabolic line. It will look like a parabolic or something like this. I don't know if my hand can do it very well. Something like this, a shape like this. Like a parabolic curve. That's what we're going to have as the unit. So this will give us a negative moment. You can also shade if you wish. Also shade it if you wish. So at this point is 100. So this is the bending moment. So this is what we're having. The bending moment diagram, the shear force diagram for this problem. So the next problem we're going to example 3. Example 3. So the next example we're looking at now is a case of a combination of a point load and a uniformly distributed load. A point load and a uniformly distributed load. So please ensure you know what we are doing here. We are just learning how to draw bending moment and shear forces diagram for a cantilever beam. That's what we are looking at. Although we are still going to look at in our next section, we'll be looking at how to draw bending moment and shear force diagram for a simply supported beams. So let's look at this question now. The question is the diagram for the cantilever beam shown below. Draw the bending moment and shear force diagram. That's the question. So I already told you the first thing you do is to draw out the free body diagram, which is just to show the forces acting in the beam. So what is forces acting here? We have horizontal force, although it's latent, there's no horizontal loading. Horizontal for point, let's go to point A, let's go to point B, let's go to point C. So we have for point A, you also have the vertical reaction for point A, vertical reaction for point A. Then we also have the bending moment at point A, because this feet support can resist bending moment, and bending moment at point A. So the next thing, we will now represent the beam with just a straight line. So this is the beam. This is the beam, and at this first point, we have 5 kilonewtons. This other point, we have 4 kilonewtons. And between these two loadings, we have a uniform distributed load, which is 3 kilonewtons. per meter. And what is the distance from here to here? 0.5 meters. From here to here is still half. That is 0.5 meters. So that's what we have. That's what we have. Now, as well as from here to here, from this place to this place should be we're having 0.5, that is 1 meter. That's what we have here. So upward forces must be equal to downward forces for equilibrium to be certain. So what is our upward force? Arrow AV, that is arrow VA. Our upward force must be equal to downward forces is 5 plus 4 plus this one is coming down. This is distributed load. Remember how we do convert distributed load to point load. We use the load to multiply the span. This was 0.5. If we do this, what are we going to have? So this times this, that's going to give us 1.5. This plus that is 9. 9 plus 1.5, I'm going to have 10.5. That's going to have 10.5 kilonewtons. So I'm going to have 10.5 kilonewtons. So the next thing is to calculate the shear force at each point. The shear force at each point. Let's obtain the shear force at each point. So let's go. For point B, what is shear force at point B? Like I told you, you should start from the free end. It's very important to start from the free end. So what will be the shear force at point B? So for point B now, the shear force is coming downward. So let's say minus 5 kilonewtons. That is the shear force at point B. Then the shear force from B to C. The shear force from B to C will be minus 5. That's already at B. Then plus this one that's going from here to here is what? Minus 3 times 0.5. So that's going to give us minus 5. 3 times 0.5 will give us 1.5. That is going to give us minus 6.5. That's what I'm going to have. Kilonewtons. So I'm going to have for that. And then minus and plus will give us minus. Next, the shear force. The shear force at point C will now be equal to the shear force at point C will be equal to minus the shear force from B to C is already minus 6.5. Then plus what is the force at point C? Minus 4. That will give us minus 10.5 kilonewtons. That's what I'm going to have. Then the shear force from C to A. Shear force from C to A. From this place there's no load. So from C to A is still minus 10.5 kilonewtons. Then the shear force at point A now will be equal to. Now when you get to point A, there's a vertical load going up, which is equivalent to 10.5. So we now have minus 10.5 plus 10.5. But this one going up to be positive, and that will end it at 0 kilonewtons. That is shear force in distribution. So it must end. If it's not ending, it means there's a problem somewhere. Now let's look at the bending moment. The bending moment. The bending moment. Let's see what I'm going to have. Moment. For the bending moment, that's what we're going to have. The bending moment at point B. We're going to have point B. Look at this. There's a force here. Can you see it? Yeah, there's a force there. But the problem is there's no distance between the force and the point. So there's no distance, and we require distance for bending moment. The bending moment at that point will be 0 kilonewtons meters. What is the bending moment at point? Just like the bending moment at each point is point A, point B, point C. What is the bending moment at point C? What will be the bending moment at point C? Now, two loads are going to contribute to this moment, which is 5 and this. Then this 3 distributed, that is the 3 kilonewtons per meter. So how are we going to do that? So this is going to give us, guys, this times this distance between B and C. That is minus 5 times. What is going to do this and this? That is 0.5 plus the moment that's coming from this uniformly distributed load, and that will be we can convert it to force. So to convert it to force, we can use this load to multiply the distance is 0.5. The first thing we do, divide the force. Now, the force will not be acting at the center. The force will be acting at the center. What will not be the center of 0.5? That is 0.5 over 2. 2 times. Now, the distance between this center and this place will be 0.5 divided by 2. That will be times 0.5 over 2. So that's what I do have. So that is the distance. That is the vertical distance between the center and this place. So, but if you solve that, what I'm going to have. So from your cash calculator, because this is coming a little bit complex, a lot of time, cannot be resolving that like that. So let's just solve it to a cash calculator. So we're going to be having. So what we're having here now is 0.5 times 5, then 3 times 0.5 times 0.5 over 2, 0.5 over 2. So I'm having minus 2.875 kilonewtons meters. That's what that is the bending moment I'm having at this point. So let's calculate the bending moment at point A now. Because the bending at where the shear force is 0 should be maximum. So let's calculate that should be the maximum. That should tell us whether we are correct or not. But the moment at where the shear force was 0 at this point A, the bending should be maximum at that point. So let's check. Let's bend the moment at point A. The bending at point A will not be. Now for the first 5 minus, that's 5 times. That's 5 times. What's wrong between the 5 and this point? That's 1. 5 times 1. Then plus minus 3. Minus 3 times. What is the distance of this? What is the span of the load? 0.5. 0.5. And what is the perpendicular distance between the half of this load to this point? That will be from here to here plus half of this. That's 0.5 times 0.5 plus 0.5 over 2. That's what I'm going to have. This half plus from here to here. That is distance from here to this half. So plus 44 times this, that is 4 times 0.5 plus 4 times 0.5 times 0.5. So what next thing I'm going to have this place? What next thing I'm going to have this place? So we're going to be having something like this. We'll be having 5 times that's already 1. So let me just do it so just do what we are doing. That will be minus 5 minus 3 times this and this other one. That's what I'm going to have. That's 3 times 0.5 times 0.5 plus 0.5 over 2, 0.5 over 2. So you can solve it to your actual calculator so that you know what we are doing. So that's going to give us minus 1.125. Then minus times plus will still give us minus. That is going to give us minus 4 times 0.5 is going to give us 2. That will give us 2. So this one is going to give us something 8.125. That's what we're going to have there. So let's just confirm it. See what we have. So we're going to have 8.125. So I'm having minus 8.125 kilonewtons meters. So let us confirm it again. So those that we are in order. That's minus 5 times 1 minus 5 times 1 and minus 3. 3 times 0.5 times 0.5 plus half of 0.5 over 2, 0.5 over 2, then plus, okay, that's minus 4 times 0.5. So I'm having 8.125. Yeah, we are correct. So this will be the bending moment at point A. So the next thing, let's draw out the bending moment and shear force diagram. Let's draw out the bending moment and shear force diagram. First thing, you draw the load. Draw the diagram. And the first thing, you draw out the diagram. Draw the diagram. The first thing you do, draw the diagram. Then we have a load here. We have another load in this case. So the first load is 4 kilonewtons. Then the second load is 5 kilonewtons. Then we have a different display load of which is 3 kilonewtons per meter. So So from here to here, I just withdrawing the formal diagram, 0.5 meters, 0.5 meters. So that's what we have. So I just put the construction line downward, draw some construction line downward. From each point, this point A, point B, and C, just draw out some construction lines that are very important. So that's what you do. Somehow important. The next thing, let's draw for the shear force. We draw out our beam or horizontal line to represent the beam. The next thing you do is to start calculating. At this point B, our shear force was -5. So just say, okay, let's say from here to here is -5. Mark. From that, that's -5 kilonewtons. So you mark. So from B to C, the shear force now moves to -6.5. So at point C, from B to C, it moves to -6.5. Let's say here will be -6.5 kilonewtons. So you mark it. Then at point C, it will move to 10. So at point C, it now draw to 10. And draw to 10. So just there's no need of putting negative because the downside is very negative. Now move to 10 kilonewtons. Then from C to A, it will see 10. So you mark, it will see 10 kilonewtons. Then from A, it moves to 0. So you mark, I see. So the next thing you draw, remember, if it is a point load, you just draw them with a straight line that is not a diagonal. A straight line that is not a diagonal. It don't look like a diagonal or an inclined line. It's not inclined to any stops. But if it's a distributed load, we are going to draw it an inclined line. A line that's somehow inclined, but it's still straight for shear force. So let's join and see. We're going to join. This is the point load. But from here to here, the distributed load will supersede the point load. So we're going to draw the straight line, but in form of a diagonal. So we're going to meet it at this point. So this point will now be 6.5 kilonewtons. Then from here to here was a point load, still join. Then from here to here, still point load. The point load is still going to still join. So you join it together. So the next thing, ensure that the line is straight. It's very important. The next thing, you join these two. So this still, here still 10 kilonewtons, and you end it. Just join it. So we'll have negative shear force. So you just shield it if you wish. So this will give our shear force that will be our shear force diagram. Then the next one is for bending moment. Bending moment diagram. The same way we draw a line. Our position line is already here. We draw a line. Remember, we draw the positive movement to the negative movement to the positive y-axis, then positive movement to the negative y-axis. So let's check. That's what we're going to have at point that is 0 at point the movement was 0. Then at point C it was -2.75. So let's say okay, at this point now it will be -2.75. 875. Then at point 8 it was -8. So let's say this point will be -8. So it will be -8.125. So you just between this point and because this is then you draw with a curved line, a parabolic line. Okay, a parabolic line, just join these two curves with a parabolic line. Not a straight line, it should be a parabolic line. This should be joined with a parabolic line. Because this distributed load, then from here there's no distributed load, you can just join with a straight line. Join this with a straight line. For point load, you join with a straight line, but it will be a form of diagonal for movement. You can straight, just a straight line, but then it's parabolic. And join this together. So this will give us negative movement. Then we will have, this should be our bending moment diagram. So this is how we draw bending moment diagram and shear forces diagram for a cantilever beam. So please, if you have any question, you can put it in our comment section. Be sure you watch the video over and over again to get a full explanation. So see you guys in our next class. Thank you.